All right, awesome. So I think everyone's here, so let's get started. Today the game plan is this. I'm going to start talking and give you guys a little bit more taste of a different variety of neural network models. So earlier we talked about neural network model, convolutional neural network model, recurrent neural network model. So you guys have these three models that you know, that you've heard of on a first name basis. And we walk through all the math, right? So hopefully when I say a loss function or when I say backward propagation, you guys know what I'm talking about, at least on a first name basis. So that's where I hope where everybody is. And today we're going to build upon that. And we're going to introduce a couple more models. We're going to probably start with autoencoder, and then we're going to jump ahead to image segmentation, generalized adversarial network. And I'm going to give you guys a little bit of sequence to sequence model. So we're going to talk about 4 additional models today. We're going to walk through the code. There's not going to be a whole lot of math going on. And I'm going to share all this with you guys. It's online, it's on YouTube, it's everywhere. So this way, you guys know that neural network is not just about pictures, and it's not just about making a classification, anything like that. As a matter of fact, the stuff that people do right now, it's way ahead, way ahead of just classification. So I just want to bring that on the table, which then also raises another problem, right? It means what? It means, when you guys get into the industry, you guys are gonna have to, know all of this, right? So it kind of raises the bar a little bit higher, just simply because this field is constantly moving forward, and there are constantly people developing new models. So that's that. And then the second thing I want to say before I share my screen is, when I introduce these models, my recommendation is, don't try to just hardcore memorize all of them, right? Think about the intuition and think about just really let your imagination go, right? Because none of these models people have any theory behind it, really. None of these models people know what they're doing when they created this. They have some sort of vague idea and they created it. So it kind of feels like that. And the correct way, or not the correct way, a more realistic feeling for you guys, before you learn this, and I'm going to tell you guys right now, is think about what picture you want to paint. Okay, you have a complete blank paper in front of you, a complete white canvas in front of you. You can paint whatever you want. Okay, you can draw a tree, you can draw a person, you can draw a landscape, you can do whatever you want. Okay, if I give you that scenario, I say, hey, go draw a graph, draw a picture. Okay, then you're not gonna think about you're not gonna be like, oh yeah, this picture is gonna sell me millions of dollars. That's not where you're coming from. When you're trying to draw a picture, really what you're trying to do is you look back in your life and it's like a reflection of your memory, and a memory can be either happy or sad. Okay, usually it's like that. So when I introduce this model, I'm gonna share screen in just a few seconds. I want you guys to be in that mental state, and I'm just gonna tell you guys this right now. If you feel like the best models that ever developed by mankind, it's when they're in this mental state. Okay, it's not like by money or by other incentive. It's because that's the model innately coming from their heart, right? So it's an art piece. So I want to set that tone in front of you guys, and now I'm going to share my screen. So give me just 1 sec. All right. So this first type of model I'm going to tell you guys is called an autoencoder. An autoencoder, as its name suggests, you're gonna kind of have an encode and decode process. So the encode and decode process, don't get intimidated by the name, right? It's just a 2 separate neural network architecture such that the dimension changes. That's really it. That's really it. In terms of exactly what you want to do in the encoder, that's completely up to you. You can have a convolution layer, you can have dense layer, you can do whatever other things that you want to do. Normalization, all up to you. Those things doesn't matter. You can tune it later. But the key point to distinguish encoder and decoder is the dimensions. So for example, you have a picture. This is a famous picture coming from MNIST dataset. MNIST dataset is the handwritten digits. There are pictures that are size 28 by 28. And you send these pictures into a network. What's going to do is it's going to go to encoder first. What encoder does, it shrinks the dimension, right? So let me draw it out. Maybe that will ring the bell a little bit. So let's say you have a picture coming in. That's a level 2. and then it comes into a network. And then the first thing is you have maybe a neural network layer that has a lot of neurons, right? Let's give a concrete number. What is a lot? A lot can be 128. And then you go through another layer, and then the dimension reduces. Okay, so really you can pick whatever you want, but typically people just divide it by 2. So it's always a multiple of 2, more or less. And then you can keep going. Exactly how many layers, that's all up to you. It's all tuning parameters. And then once you're here, you have this thing called a latent layer. And then after latent layer, you increase the dimension. And if you're increasing dimension, then that is called a decoder. And I'm not going to draw all of them out. I'm just going to do a couple of dots. At the end of the day, you're going to realize in the last layer, the number of neurons matches the number of pixels in whatever image that you're trying to reconstruct. Okay, in this case, the data set is 28 by 28. So what that means is this is 28, this is 28, then 28 squared, that is going to give you 784. So that's exactly how many neurons in the last layer. And then you can reconstruct this picture that looks like a number 2. So in other words, the autoencoder is the type of neural network architecture that learns the intrinsic representation of the image itself. So in other words, it is not really trying to say, oh yeah, tomorrow's stock price is whatever, right? It's not trying to say, oh yeah, this picture is a cat or dogs, right? It's not really a regression problem. It's not really a classification problem. It's something else, okay? It's a completely different universe, all right? So exactly what is it doing? Well, it's learning you're throwing a picture that has a handwritten digit 2, and then it goes to encoder, goes to decoder, come out, you reconstruct the picture, it better look like a handwritten digit number 2. So what's the benefit of doing all of this, right? Why do I have to spend all my energy figuring all this out and spend all my time training the neural network? What's the purpose of this? Well, it turned out that this thing in the middle is called a latent layer. And this latent layer is linearly classifiable. So if this model is well trained, and if this model is a finished training and it has a good performance, then this latent layer, you can actually take it apart, and then you can build a new model, and then you can have a prediction. And this prediction is supposed to have higher accuracy than whatever you have before. Okay, so that's kind of like a story here. Now, that being said, I actually don't think I've seen a paper that truly proved this idea. I've seen maybe a few papers that show with a handful of data sets that this can be higher accuracy, but no one has ever proved the idea that this will absolutely have higher accuracy. It's kind of like situational based. So the performance of how this latent layer work is kind of depend on your understanding of the data and how clean the data is, and where the data, what purpose does the data serve in your machine learning pipeline. All right, so that's kind of like a big picture. So either you feel like this is easy or you feel like this is hard, doesn't matter. I'm going to show you the code and you're going to understand in like 5 seconds. The code is actually not that hard. So actually, I can just jump ahead and show you this code. This is the code for autoencoder. It's as simple as that. There isn't really anything fancy about it. It's just you have dense layer, you change the neurons, that's it. It's really that simple. So a couple of things you want to be aware here of this entire chunk of code. The first thing is this is actually not a sequential API. Okay, what we're doing here is actually called a functional API, and I'm going to explain later why that's important, maybe in the next few models. But for now, just bear with me. This is called a functional API. Like remember when you guys usually do, you have something like say model equals to TensorFlow carrots on models, and then you have a sequential, right? Sequential. And then you do model.add, and then you add layers. So you can do it that way too. Here, what the recommendation is for you guys is you change the flavor of sequential API into functional API. So what is the difference? Sequential API means you are designing the neural network sequentially. It doesn't mean the sequential model people use in time series data. Okay, so they're two different things. So sequential design or sequential API means that each layer is coded line by line. So you can't jump, like you can't do anything like that. You can't save a layer in the middle and then take it downstream, or you can't make a duplicate. You can't do any of that. The layer, once it's coded, it's hard coded. It exists there and only exists there. You can't move around. Okay. So sequential API, the entire thing is a building block. You can't take it apart. Functional API is different. Functional API, each line is by itself a standalone object. So you can take it apart. You can do whatever you want. You can make a copy. You can make a skips, and downstream in the code you can call back the function. So you can do all crazy things like that. So that is really the sequential. That is really the difference between sequential API and this thing down here is a functional API. There's a very simple difference that you can tell. Functional API is called functional API because it acts as a function. Function means what? Function means you have a name of the function, and then you have a parenthesis, right? This is your input argument, and then whatever is coming out, that's your output. So a functional form looks like this. That's a functional form, right? And this functional form is what we use for each dense layer. So if you look carefully, you have dense, and then here you have a second parenthesis, okay? The second parenthesis, you toss in input image. And the input image is whatever is coming out from the previous layer. So why is there a second parenthesis here? The second parenthesis serves as the input argument for the function. Whatever function you have, it's a dense layer. Okay, so that is really the difference here, and that's really the novelty here. Besides that, everything else dense layer forward propagation, backward propagation, loss function, gradient descent, all that's the same, exactly the same. The only thing different is these numbers, they're gonna reduce the number. Reduce means you start with 28, and then 64, and then 32, and then you expand it back. So 64, 128, 74. And 74 is designed that way, because the data is 28 by 28, and 28 squared is 784. This way, you can kind of reshape the array coming out of the neural network, and then you can put them back in the image. Okay, so after you train it, you're going to get a plot like this. The first line is the original image. The second line is a reconstructed image. So as you can see, neural network has no problem reconstructing the image that you feed in. Okay, so this is kind of like the foundation building block that you have to know if you want to move on to do all sorts of computer vision stuff like deepfake, metaverse, augmented reality, all these stuff. They all build on this kind of concept. So this is kind of like a must know if your future career is somewhere. I know Facebook is trying to develop a thing called a metaverse. A metaverse is kind of like an augmented reality universe that people can interact inside of it. It really just looks like a huge Fortnite game. I don't know if you guys play Fortnite, but it's kind of just like a huge Fortnite game. And except that you don't kill people, right? You talk to each other. So that's kind of like the idea, what they're building at. I don't know if people can accept that in like the next 20, 30 years. Me personally, I thought it was a cool idea. And the next step up is if you can construct 2D image, then why don't you construct 3D image? And if you can construct 3D image, why don't you throw time in there, right? So if you can throw time in there, then you can construct, essentially reconstruct a small 3-dimensional moving universe. So that's kind of the idea here and where people are coming from. And you can't really build any of that if you miss out on this part. Okay, if this doesn't exist, none of those things exist. So that's kind of like the important part of what this is introduced here is called an autoencoder. It's essentially the first step to understand image-to-image model. And image-to-image model is quite straightforward, as its name suggests. You have a model, you send in the image, you generate the image. Okay, so that's the first thing I want to show you guys. The second thing I want to show you guys is this model called UNet. UNet is built on top of exactly what Autoencoder is doing, except that UNet is doing one more thing. UNet is adding these arrows in the middle. Now, I don't know why people like to draw this as a shape of U. Me personally, if I'm drawing this, I like to draw it this way. So you have a encoder, right? Something like this. This is your encoder. And then this is your latent layer, and then you have your decoder. I think the correct way to draw this should be a skip arrow like this. They're essentially the same graph, but I don't really know why people draw, like why you have to like go down this direction. I don't understand the purpose of that. I think you can just go straight, and that's gonna essentially reconstruct an encode decode structure. And then these skip arrows, you kind of add it in later on, you know. So that's kind of my idea of how to interpret this thing called a UNet. Now, of course, you know, if you draw this direction, it kind of looks like letter U. That hence the name UNet. UNet is built for image segmentation. So what is image segmentation? If I Google it, can I Google this? Let's see. So image segmentation. It's much easier if I just Google it, show you guys a picture, than explain it. So image segmentation, that's it. So image segmentation is referring to the type of computer vision model such that I can feed in a picture or video or whatever, right? Some sort of 2D array. Then the model is able to recognize semantically which local region is different from the other part of the picture. Okay, so I'll repeat that again. The image segmentation is a type of task that, given a picture, given a video, the model is able to separate which local region is different from the other. Okay, exactly which local region, that's all based on your definition, right? You can define a person as one class, fine. Then that particular region is going to be person. You can define a car as a region. Then that particular area where it's like circle or whatever shape the car is, that's just going to be cars. And you can define whatever you want, right? That's all up to you. So this type of stuff is called computer vision. What is the model to do that? UNet. So let's take a look at UNet. UNet is exactly like this. The only thing that is a new thing that we have not talked about in class in regards to building this network architecture is called conv2D transpose. So we all know convolutional operation, right? You have a conventional convolution operation. Let's say you have 1, 1, 1, 1, 1, 1, 1, 1, 1, and then you apply this two-dimensional kernel on your picture. Then what you're supposed to do is, hey, you say, that's my kernel. That's basically a square. I'm applying on top left corner. And then once I'm done, I have this number. And then I move one column to the right, right? So we talked about this in the convolutional neural network, right? You move one column to the right. And then once you're done, you have the second number, right? And so on and so forth. You move down here once you're done with the first row, and then you move here, and then henceforth you have this number and this number. Done. The problem with this is the dimension reduces. If this is 3 by 3, then after you do all that work, this becomes 2 by 2. Now, if you keep doing this, the dimension is only going to shrink, right? It's not going to increase. So we need something that helps us increase the dimension. But then you can't just increase with dense layer by blindly adding neurons, right? You want to take advantage of the image, right? Because we talk about the image problem. There's this issue called the invariance property, right? All image problems have that. You have a bear in front of you, you have a car in front of you, you recognize a car, doesn't matter which location the car is. It could be the left-hand side of the picture, it could be the right-hand side of the picture, doesn't matter where they are, you still know it's a car, right? So it doesn't change, the object information doesn't change simply because you move somewhere else in the picture. So how to take care of that problem? Well, there's this thing called a conv2D transpose. A conv2D transpose is the exact same idea of convolutional operation, except one small trick. So you have a two-dimensional kernel, just like that, right? Exactly the same. Now you have an input image that's 2 by 2. How do you do conv2D transpose? You start with the top left corner, but you don't start with, inside of the picture frame. You start with the margin outside of the picture frame. So in other words, you start from here. Okay, so you have some sort of overlap, but only that corner is overlap. You have 3 other pixels that's outside of the margin of that original input image. So in other words, what's going to happen from here? You're going to have a 1 here, you're going to have a 1 here, you're going to have a 1 here. So the 3 pixels is outside of the picture frame. basically. So if that happens, you only have one pixel overlap. That's it. This is the only one pixel that's overlap. And then you do your usual drill, right? Element-wise matrix multiplication. What does that mean? Then just 1 times 1. So that's exactly just 1 here. And then you do the same thing. You move one column to the right. So then that's going to give you what? It's going to give you, draw a different color. I'm going to put it here, right? So this blue box, right, which is essentially here, this blue box, that is going to be where you are if you move one column to the right. And again, part of the kernel is outside of the picture frame. But the only difference is, well, here you have 2 pixels overlap. So if your 2 pixels overlap, then what is your math? Your math is 1 times 1 plus 1 times 1. It's an element-wise matrix multiplication. That's why you have 2. Okay? And then so on and so forth. Now you guys get the idea. Okay, what happens if I move one column to the right? Well, you can do that, right? You just move here. So what that means is you're going to be here. That's going to be your kernel. And then you look at the overlap. Well, there's only 1 pixel of overlap, and there's only 1 value there. So 1 times 1, that's just 1 by itself. So this way you get to 1, 2, and 1. And that is the first row. And you do the exact same thing to the second row, to the third row. Now you're going to have yourself a picture that is 3 by 3. So now you have a decoder, right? You have a decoder that is taking the advantage of the convolution operation. So now you have a decoder. So that is essentially the autoencoder, but on convolution level, right? Not just dense layer, not just the neurons, but on a convolution level. Okay, so if you Google it, you might see some other visualization, such as one of those like 3-dimensional visualization. So if I may, maybe some people draw something like this. And then coming here, you have another smaller square, maybe bigger square, and then maybe even bigger square, like this. And then they draw these skips. Okay, so that is really the essential idea of a unit. I actually think this is probably a slightly better visualization. But sometimes people draw 2-dimensional just to have, maybe a easier, intro level people draw 2-dimensional. But I actually think 3-dimensional is probably a little bit more intuitive. So that is the idea going behind units. Now let's take a look at the code, right? When we look at the code, let me see. Where's the model? UNet model. Okay, so this is the code. Okay, it might look very long and look complicated, but let me go through this just on a high level. So right off the bat, the build UNet model is actually down here, right? This is the main function. So we're gonna say this is the main function. And then you have 3 functions above here. This is actually the helper function. So I should really say helper function. The first helper function is called conv block. The conv block really just to put 2 convolution layers together. That's it, like 2 convolution layers. So you can kind of pack this entire thing together called a conv by 2. Right, so convolution do twice. Right, that's once, that's twice. Right, this entire thing is called one function, one block. So the encoder is going to call down this block, and the decoder is going to do the conv2d transpose. Okay, so the encoder is just going to call on this block, right? This function is coming from here, and then it's going to do a max pooling. Max pooling, you guys all know what that is, right? If you have a 1, 2, 3, 4, that's going to be your array, right? A 2D array. What is max pool? It's 4. It's the maximum number. Okay, so that is your encoder block. So this entire thing is called encoder by 1. And then after encoder, of course, you have to do decoder, right? Decoder is here. This is the decoder, and also this is by 1. So it's a decoder block. The only thing new here is a concatenate. Conv2d transpose. This we just talked about it. And then concatenate is the skip arrow, which is a gray arrow on 2-dimensional graph, or the skip features or skip arrows that I draw if you're on a 3-dimensional graph. So that's the concatenate. So this way, it gives you encoder, decoder, and notice that the decoder also has this concatenation here. Okay, so that is all your helper functions. So now with that being said, then let's take a look at the main function. The main function is down here, and let's take a look at the design. So first of all, you have an encoder block, so something like that. Another one here, so you draw another one, but of course it's smaller, right? Because you've done a convolution operation, the dimension reduces. And then another one, so I'm not going to bore you guys with that, but you guys get the idea. So you reduce like this. So this is what we call an encoder. And then after encoder, you need to do decoder, right? So if I may, I'm going to draw here like this. So on and so forth. Right. Now you have a decoder. Decoder, of course, you're going to start with a small dimension. So that's going to be here. Now notice that this decoder block has 2 arguments. This one is just neurons, so kind of ignore that. The second arguments come from S5. S5 is defined here. So in other words, it's also trying to draw this arrow here, okay, that is taking something from the beginning and make a duplicate and concatenate it in the decoder. So this is essentially the functional API that we're talking about, right? Why do you do functional API? Functional API allows you to take things apart and move things around and create duplicates that you can use later on in the code. So this is exactly one application of functional API. Okay, so then you can continue from here, and you guys probably get the idea. The second decoder block, right, of course, is bigger, right? Because we talked about the conv2d transpose. It increases the dimension. So increases means bigger, right? And then of course you can do that a couple of times. Every time you do it is of course bigger, right? You guys get the idea. Da 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 da, and then you're here. Right. So once you're here, don't forget the blue arrows. So let's draw that. You can have something like this. And then this. And then this blue, and then the final image here, that's going to be your reconstructed whatever image segmentation that you want to do. So in the beginning, you might have some actual pattern here, right? Some actual pattern here, whatever pattern that is. But in the end, you're going to have a region, and the region is blurred out. Something like this. And this will tell you exactly, that's a car in the middle picture, so that area, I'm going to use one color. Everybody else, that's different color. Or if it's a person, then it's a person region, that's one color. Everything else is a different color. So that's essentially how UNet is built. Really, I think the key idea is to, this eventually you flush it out, but I think the key idea is actually to truly understand the decoder block. Based on my experience, I think most people get stuck here. The code itself is not hard. It's just 2 lines of code. conv2d transpose, concatenate, and then you're done. The code itself is not hard. The way that it can be hard is if you are implementing your own datasets, and your dataset is whatever dimension that is different from what this is doing, then you need to work out dimension. When you reduce the dimension, that's not hard. You just reduce it. People don't really put too much attention on the output dimension. They kind of just take a look in the end, right? However, if you're doing UNet, you can't just wait for it to compile because it may or may not work, right? So each step of the way, you kind of have to keep track on dimension. Otherwise, this code is going to run into a bug. So that's really the difference here. So once you work out the model, let me see, I have an output here. It kind of looks like, I don't know how to pick out, here's a good picture. It kind of looks like this. So in this data set, let's say it's a ship, right? I just took one color out. It's RGB, right? I just took the average of RGB, and then I essentially look at the binary mask. So it could look like this, or it could look like this. So kind of like the shape of where the boat is. And then if you work out the model and you do a prediction, I have a prediction down here. It will essentially, the last column is a prediction. So as you can see, it's kind of it's actually pretty close to the third column, which is the mask. So this kind of stuff you can definitely create using this image segmentation called UNet. I believe this picture here, that's a frog. If you look at the average of RGB, it's kind of blurred out. And it can turn into binary. You have maybe some tree leaves here and a frog body is in the middle. And if you do UNet, it has no problem learning where that shape is in the center of the picture. So this is basically like kind of the idea that you can take advantage of when it comes to image segmentation. All right, so that's essentially about UNet. The next thing I want to show you guys is, I think somebody else mentioned this earlier in the class. I forgot which one. I think it's maybe like last week or something. Somebody mentioned this idea called a generalized adversarial network. So a generalized adversarial network, or you may call it GAN, G-A-N, that's 3 letters, GAN. It's essentially referring to two models. The first model is called a generator. The second model is called a discriminator. The generator is trying to create some picture. It can be good, can be bad, doesn't matter, right? It's creating something. It's a picture. The discriminator is going to say, this picture, I know it, or this picture, I don't know it. Exactly what you know, that's all up to your definition, right? It's dependent on the data scientist. You can train the generator to, you can train the discriminator to recognize which handwritten digit is this. Or you can train the discriminator to recognize if I unlock my, if I take my iPhone in front of me, is it going to recognize my face, right? How does it know to unlock if I just look at the screen, right? So all that stuff, it's based on your definition, okay? So if your goal is to unlock your iPhone, right, then you can train the discriminator to recognize that's your face. Then you just throw in the training data set that's your face, right? Plain and simple. So that is the idea going behind a generalized adversarial network. So now let's talk a little bit about how they're doing this. Let's see. Okay, so this is the code of how they're doing it. And let me quickly walk through this. So when it comes to a generator, it's, I don't want to say exactly the same as a convolution neural network, but it shares similar philosophy, So the idea is this. I know that in the end of the day, I want to reconstruct the picture, right? So if I look at this model, whatever's coming in the end better be a picture. That's why we assert, this assert function means you check it. So if it's wrong, if this is not equal, it's going to give you an error message. So it's kind of nice to tell me, hey, is the model correct? Is the model not correct? Well, we have this line code tell us that's the case. So this checks that if the model finally is producing something that is this dimension. Okay, so what is this dimension? This dimension means 28 by 28. So down here, it needs to be already here. So this needs to be something like this. Then that's 28 by 28. This one just a grayscale. So RGB is 3, right? It's a red, green, blue. That's 3 colors. Grayscale just by 1. That's really it. That's really what you want to predict. If you can predict this one, if you can produce this one, then the generator is good to go, right? In the beginning, it's some sort of random noise. So this is a dense layer. It starts with just one vector. Okay, just one vector here. That's complete noise. So you have complete noise coming into the architecture, and then you do what you do, right? Conv to the transpose. Same concept, right? Same philosophy. So what does it do? Well, you look at the picture, you take advantage of a convolution operation, but the dimension increases. So that's how it's able to get from a numerical value to a picture. So dimension increases, then looks like this, then looks like this, then looks like this, right? Exactly how many layers you do in the middle, that's completely up to you, right? Completely up to you. I can take this chunk of code, copy it 5 times if I want to, right? But of course, you're gonna have to work out the math. If I want to do that, you're gonna have deeper layers, but this dimension is also gonna be bigger. So it might be too large for your image to fit, right? That's a problem. So then what do? Well, you can reduce the kernel size. Okay, so all that's up to your own design. You can do whatever you want, right? Really let your imagination fly, right? Let your imagination fly. So this is what we call the generator, right? And once you finish this, that's like 50% of the model. Now we need to work out the discriminator, okay? So discriminator, let me scroll down. It's here. That's the discriminator. The discriminator is essentially saying, hey, you have a picture, right? Why don't we just start doing convolutional neural network? So picture coming here. First thing you do is a conv2d, and that's it. It's conv2d. So if you do conv2d, the size drops, right? You reduce the size. And then same thing, you can do it 2 times, 3 times. All that's up to you, right? That's up to you. And then in the end, you flatten it, right? So that will become a big vector, and then you can do a dense layer. And notice that here, maybe I need to erase this so you guys can see. The last number, it's what? It's 1, right? It's number 1. 1 means what? 1 means a number, right? So after so many dense layers, whatever you want, you have 1 number here, 1 neuron, okay? So what is 1? This 1 is some sort of score. And then people are like, okay, what score are we talking about? Well, that's up to you. That's really up to you. You can define a score as similarity. That's fine. You can define a score as, is this my face in front of camera or not? That's also fine. It's all up to you, okay? But in this case, typically what people do is the score is some sort of similarity score. Basically what that means is you compare 2 pictures. If the numerical value is small, then the 2 pictures look close to each other. If the numerical value is high, then maybe they're not that close. So all those definitions complete up to you. Typically, on a common practice, that's what people tend to do, which is similarity score. So, so this really requires a little bit of imagination. And if you look carefully, right, the generalized adversarial network is kind of like autoencoder, but you take the encode decode and you swap a position. So that's kind of what it feels. So let me write that down. Just give you guys a so let's see. So autoencoder. This is autoencoder. So it shrink and then increase, right? But if you look at the GAN, this is a GAN. So it will increase 1 number, it will increase, and then it will take this, send it to the discriminator, and then it will decrease, and it's 1 number. So in the beginning, it's 1 number, in the middle, it expands, and then in the end, it's 1 number. Versus in autoencoder, in the beginning and the end, it's a large number, but in the middle, it's a small number. Okay, so that's the difference. So really, it's just you take autoencoder, you take it apart, and you swap the position. So that is what GAN is doing. Okay. After that, I think that's really it. That's really all there is about the design of a generalized adversarial network. What I really want to point out is the training process. I think the training process might be a little bit outside the scope of this class, and I'm trying not to confuse people, but I'll just quickly walk through what that is doing. So the generator loss is really just a cross entropy. Okay, it's really just cross entropy. And we talk about cross entropy, right? It's a log loss. So what is cross entropy? Remember that the function that we talk about like this, right? This is 0, this is 1. And then if you're here, then you're good to go, right? This is a good model. If you're here, this value here, then you're a bad model, right? And that's it. This is exactly what this is. Really, that's it. So this function here, if you can understand that, then you have no problem understanding this because they're the exact same thing. Okay. So that is the cross entropy is kind of like the unit loss function design that we use for both machines. The generator and the discriminator, they both use cross entropy. So you see cross entropy here and here and here. Okay, so that is the building block. Now, one last piece of puzzle that I want to tell you guys is the one unique thing about discriminator is that there's 2 components, right? So if you look carefully, there's this component and then there's this component. So the final loss is going to be those 2 things add together, okay? Why do people do things this way? Discriminator needs to be able to tell what is real, what is fake, right? If you just compute the real, or if you just compute the fake, how is it supposed to tell? You can't, right? So when you train the model, you better tell the computer the both real and the fake scenario. So the loss function is going to be the 2 numbers add together. Okay, so that is really what's happening here. And then it actually took a lot of people some time to understand these two lines of code here. This is a 1's like, and this is 0's like. The 1's like, I have a sample function here. The 1's like just give you some sort of array that is all numerical value 1's, right? Exactly like this, numerical value 1's. The 0 like is an array that's all 0's. So here, this paragraph is essentially the core of how people design the loss function for discriminator. The discriminator needs to tell if the pictures are real or fake based on your definition. In this case, the common practice is the real picture, you can simply compare that to 1 because we define 1 as real, versus the fake pictures, you can compare that to 0 because 0 we pretend that's fake. You're real or fake, right? So 1's or 0's. So that's kind of how things work. That's why there are two pieces of puzzle that you put together to form this total loss. That's final outcome for the discriminator. All right, and this way the discriminator is able to tell from both scenarios, right? You don't want to just have some sort of AI camera in front of your door, and you don't want to just have the capability to say that this person doesn't belong here, right? You also want to have the capability to say that this person belongs here, right? Because I wanna go out to my home. The camera needs to let me in. So you need to have both capabilities, right? If it's me, you need to let me in. If it's a bad guy and this guy doesn't leave my house, you need to close the door, right? So you need to have it's two separate functions, okay? And this real loss and fake loss just take care of that problem for us. And you need to tell the computer, this is the real loss, this is the fake loss, and that's what the loss happened together. So that is the discriminator loss here in terms of this design. And with that being said, now you are at one final step, which is the training step. This training step, I'm pretty sure this is going to be what's confusing people, which is this is what we do. This is what's going behind that model.fit function. So this entire script, you're not going to see a single model.fit. And the reason is because we are taking that model.fit apart and we're coding that from scratch by ourselves. So what's happening is this model.fit. Like recall this function, right? And then you throw in x, you throw in y. Done. It's all automated for you. Well, that's true for convolutional neural network, for recurrent neural network, but in this case, unfortunately, it can't take care of that. It can't do that for you. Okay, so this is not going to work here. You need to code. You need to take this function apart and code the training step by yourself. So this really requires you to understand what is gradient descent. Okay, and this is where the math is important, because if you lose out on the math, then this line of code is not going to make too much sense. So I would say that the key concept of understanding this code is actually not computer science. It's actually your intuition to understand the gradient descent algorithm, which is really a calculus problem, and then it boils down to just a math problem. You should know how to take a derivative, and the derivative needs to make sense to you. Like, I'm not talking about getting high grades. I'm talking about derivative of a function really needs to make sense to you. Like, when you look at it, you need to feel it in your bones. Okay, so that's what I want to say about this training step function. So we can briefly walk through this. First things first is there is a noise. That's one of the arguments. Second thing is there's a picture. Okay, so these are the two arguments that this function requires, right? Two inputs, image and noise. Image is whatever in your training data, right? You need to have training data. It's a bunch of pictures. That's your image. The noise is essentially drawn from normal distribution. So normal distribution is the standard statistical distribution function that people use to create noise. It basically means there's no pattern, right? There's no pattern. It doesn't tell us anything. Right? So that is the start. If I feed in the noise, the model is supposed to give me an output that's completely random. That's what noise means, random. Okay, so what's happening here is there's a generator first. Okay, so you throw the noise into the generator here, and then it produces some sort of picture, right? So what is the architecture? You have a noise, and then you send to the generator, and then it increases the dimension and then it becomes a picture. The picture could be a complete random, but you can also draw some pattern, right? In the beginning, chances are it's drawing something complete random because the model hasn't learned anything yet, right? So it's complete random. But that's okay, right? That's where the discriminator is coming in to tell the model, hey, this is wrong, this is no good, this is good, right? It's telling the computer that. So the discriminator comes in. You need to call the discriminator function twice. The first one is on the real image. That's a bad drawing. Let me switch to different color. The first one is on the real image. So this is coming from this argument here. The second one, let me switch to a different color. The second one comes from the generated image. So it's here. Generated image. So then what does that do for you? What that means is you're gonna have yourself a real picture and a fake picture. Okay? And the discriminator need to say the real picture is this, the fake picture is this, that's the difference. So you need to tell us that, right? How do you know to tell us that? You use a loss function. So that is why here we have a generator loss and here we have a discriminator loss. And both of these loss functions we talked about above, we define those above, that will give us two numbers, right? The gen loss and the disc loss. So in this way, what you basically do is you take this picture and you send to the discriminator. It's going to reduce smaller, smaller, and now it becomes one number. And as this is one number, the discriminator is going to be like, is it good or bad, right? Good or bad, right? It's going to tell us that. And once you tell us good or bad, then we do our gradient descent. So what that means is you need to compute the gradient. So all that junk, right? Partial derivative, nabla, right? Whatever gradient that we do, right? Whatever chain rule that we take, right? All that junk is packed into this function called gen tape. And for discrimination, there's a disc tape. Okay, so these two things are defined as tf.gradient tape. Gradient tape basically means I give you a function, you take the derivative. Basically, you look at the changes with respect to each parameter. So it kind of feels like a giant array of list of numbers that tells the computer, if this w changes this little, this much, then the loss function changes this much, and that is a gradient. So once you have two gradients, you apply the gradients, then you're done. This entire thing is called a one step. Okay, so this is a one step. So this entire function is one step. So you in model.fit, you see a bunch of epoch, right? Like epoch 1, you train it give you accuracy. And then epoch 2, it give you accuracy, and so on and so forth, right? So this entire thing, you can call that one epoch, right? This entire thing is one epoch. The only difference is here, we code each line by line by us. We don't rely on model.fit, okay? So that is really the difference here. So now you have one step, right? You have one step. What's next? You do all of them, right? So then you use this one function as a building block, and you're going to plug into this train function. And this is actually much easier to understand. Really, you have epoch. Epoch is going to start with 1, 2, 3, 4, right? It's gonna keep training. And every time you train, guess what? You need a new set of pictures, right? So that's why you have a second for loop to check every picture inside of the dataset, your dataset. And dataset is essentially whatever training sample pictures that you provide to the function, which is why this train function takes two arguments. One is dataset, and the other one is epoch. You need to tell the computer, hey, I want 50 epoch, or hey, I want 100 epoch. Then the first for loop is going to take care of that. The second for loop is going to take care of each of the picture. And each of the picture you train it, you will get more and more accurate. Because every time in the for loop, we call this training set function, and the training set function is coming from here. You plug in there. And that's really it. So really, the training stops here. Everything below is kind of just like making my production pipeline a little bit cleaner, all these nice pictures, animations, so on and so forth. So all of this is going to give you a GIF file, GIF, and let's take a look at the performance. So scroll down, it will look like this. So this is actually a GIF file, and as the epoch increases, you can see that the numbers are looking more and more like these handwritten digits. When the epoch is 0, 1, 2, 3, you're not going to know what this is. It's like complete random scrambles, right? But when the epoch gets to 30, 40, 50, you can kind of tell, that's number 4, or maybe that's number 5. I don't know, maybe that's 7, maybe that's 9, maybe that's 7, maybe that's 9. Now you guys get the idea, right? As the epoch increases, the computer is learning to generate fake images that look like actually handwritten digits image. So that is the power of this type of neural network called GAN, Generalized Adversarial Network. So that is pretty much everything I want to show in regards to image-to-image models, which is the next step up from convolutional neural network. And then there's also this thing called music generation. I don't know if I have time to cover this, but I can just show you the outcome real fast. So the music generation is essentially taking advantage of recurrent neural network, and you're sending a time series data and you're producing a time series data. Okay, so the sequence to sequence. So in other words, basically what's happening in this entire script is you have music, right? I don't know how to draw music, so I'm going to draw something random. I should really pay attention to what I'm doing in like the music theory class. Do, re, mi, maybe that's mi is over there, right? That's C, D, E. So this is E. C, D, E, F. This is F. C, D, E, F, G. That's A. C, D, E, F, G, A, B. So that's B. Right? That's basically music theory. And then each of this corresponds to what? A letter, right? And then this is going to be the data that you use. Okay, you send it into an RNN, recurrent neural network, and then it's learning to produce a sequence. So I'm out of space, so I'm drawing here. So it's learning to produce a sequence. If the music is E, F, G, A, B, then it needs to learn to predict something, right? And in this case, it's going to be some sort of letters. So each letter corresponds to a number, and we talked about that, right? In language problem, each letter corresponds to a number, or whatever, right? Each word can correspond to a number as well. So those numbers are what we throw into an RNN, and RNN can produce us back a bunch of different numbers. And those numbers, you can translate that into these notes. So in other words, what's happening here is this. Let me get rid of these drawings. So first of all, you need to take these notes and convert that into tokens. So into numbers, 1, 2, 3. And then you send that into an RNN. And RNN is going to predict 4, 5, 6. And 4, 5, 6, you need to go back to dictionary and recover what note that is. So you can draw these lines. It should be 5 lines, right? And then 4, 5, 6, maybe that translates to whatever's happening here. Let's say that's B, do, re, mi, fa, sol, la, ti, do. Okay, so this is C. So somewhere here, C, and this is D, C, D, E. So this is E, right? That's the notes. So this is the data. It's something that actually people wrote, right? This is generated by AI. So this entire architecture is called music generation, right? Basically what that means is AI is learning to write a chunk of music that is based on the training sample. If the training sample is classical music, chances are it sounds like classical music. If the training sample is Michael Jackson, chances are it's going to sound like Michael Jackson, okay? If the training sample is complete random, then it's complete random, right? That's the story. All right, so let's take a look at the performance. Where's my data? That's my data. Right, so this is my data. I'm gonna make sure my sound is up. Right, so that's the training data, okay? And the computer is going to take this training data, look at the nodes. The nodes essentially look like this: A, B, C, D, F, D, F, A, D, whatever, right? The nodes look like this. Translate that into numbers. Numbers sent to RNN. RNN produce the numbers. Numbers go back to the music nodes, and let's take a look at the outcome. The playback is somewhere down here. Where's the playback? Oh man, did I not have it? Yeah, it's one of these. It's one of these code. Sorry, let me run it during the break. Let's take a break. Let's take 10-minute break. Let's come back. I'll run this code during the break, and I'll show you guys what the output sounds like. And then we're going to break out. So I'll see you guys in 10 minutes. All right. So I already went to the code, and once again, what happened, right? So you have the music data. These are letters. Each letter corresponds to a particular music note. E, C, B, F, G, A, B. And then these music notes gonna be represented as letters, and then the letters will be translated into numbers. The numbers then go into RNN, and then RNN produce new numbers, and new numbers refer back to music notes. So here I trained, how much did I train? I trained 1,000 notes. 1,000 notes turned out to be, how many songs it did? It ends up being 3 songs. Not all of the songs are correct. I think they check the format, and the format is incorrect, then they don't do it. So there's some formatting thing in the beginning that they check, and then end up being 3 songs. So what is the training data? The training data is essentially something look like this. So you guys get the idea, right? That's the training data. And then the test data is what I have down here. This is the first song that's generated by machine, okay? So that's the first song. And then there's a second song here. I'll play that. And then there's a third song. So you guys get the idea, right? I don't know if people like the song. Me particularly, I didn't really detect any rhythm. I thought that was one thing I don't like about it. But then if you go back and hear again the training data kind of all sounds the same. So I'll play again. So it kind of sounds similar, except that maybe it follows more scales than what the AI predicted. So my conjecture is when you are at the level of composing music, you should be pretty familiar with the music theory, like all the scales and how the scales can change, what are the variations. You should be very familiar with all of that. So when a human composer writes a piece of music, they're taking that into consideration, right? Because you go to school for this stuff, right? You can't just magically write music. And chances are there's some rules going behind it. Is the data rich enough for the AI to learn about that rule? That's a question. No one knows the answer to that question. Okay, we don't know. Maybe it can learn. Maybe it can learn. We don't know that. But one thing that's for certain is, whatever it is, AI is somehow able to reproduce something similar to the music. At least sounds similar. Maybe it doesn't follow the rules, but it sounds similar. And that's one of the biggest debates behind, whether you saw on TV or whatever you saw on the internet. Is AI truly able to write music, write poems, or whatever, draw a picture, right? Is AI truly able to do that, or is it all just about pattern recognition, right? Does it actually have like soul and memory behind it? Right? What's a spirit, right? Unfortunately, AI doesn't have spirit or soul or anything like that. As of what we're doing right now, it is the computer science community agree upon more towards the answer that AI is really what it's doing is just pattern recognition. If you give me a training data set that you play the note C very often, the output is just going to learn to play that very often. And then you name it, right? If you play do re mi very often, then it's just going to be do re mi very often. So it kind of feels like that, which really just about, hey, whatever human repeated, I'm just going to learn to do that. So that's kind of what it feels like right now. Is AI truly able to learn like the memory, the happiness or whatever, like the sadness behind when the composer is writing a song? Is a yes or no? We don't know. It's not a strict no answer. It's whether it's yes or no. We don't know that. Okay. So that's kind of what's going on here. Now that being said, a lot of these debates really comes down to essentially two different groups of people, right? If you put a poet, and a computer scientist together, and you let them debate, then that kind of boils down to, does AI have soul or spirit sort of thing? Does AI have memories? That sort of thing, or is it merely just about pattern recognition? On a practical level, because I've been working in the industry for a couple of years, on a practical level, I think these things are more like a good TV show story. In practice, I've almost never seen anybody trying to say AI has souls. Now, that was never even part of the question. If it even makes into a list of questions, okay. So in practice, it's all about is AI accurate, and if it is accurate, how do we explain the predictions? And if a prediction go wrong, if I have a new data set, what is the contingency plan? So in practice, like I'm not talking about like movies or TV shows, right? In practice, how AI is used is actually fairly different than what's being portrayed on the internet, right? So I just want to say that to you guys, and this way it kind of gives you guys a playground, right? If you want to throw in some of your own music, try it out, feel free to do that. You want to try out your own pictures, feel free to do that, right? You take a bunch of cell phone pictures, load it on Python, see if the neural network can reproduce it. So all that stuff is doable for you right now. The code is here. You just use it, right? So with that being said, that's everything I want to say. I don't want to take too much of time anymore. So Sam, whenever you're ready, have breakout room open. Yeah, and everyone, whenever you see a breakout room, just join there and finish the project. Yeah. Right. So in terms of projects, by today it's Thursday. Tomorrow is Friday. So what that means is hopefully most of your projects is like 90% finished. Let me know if you have questions. I'll stay over in case people have questions. But in regards to projects, by today, hopefully you run through all the code, you have some results. It can be good, can be bad, doesn't matter. As long as you have a story to tell, you try different things, and you have a comparison, then that's what we're looking for. You're not responsible for producing like a world-class performance, right? 100%, right? That's not the purpose of the class. So that's number one, right? Have different results. I prefer you try out different models than you try one model and maybe get better performance, so like finger crossed, right? So I prefer you try different models and have a comparison. So this way you can touch upon different things. All right, so that's one. And in regards to projects, the second thing about projects is obviously slides ready, right? And then the second thing we look for in terms of this session is going to be the GitHub repo. So somebody asked me a question about GitHub repo. If you still have questions, let me know. And of course, I'll stay over, in case people have questions, I'll walk you through what's going on. GitHub repo, the bare minimum requirement is you download the Python notebook, you do your PowerPoint, you upload them on GitHub. So whenever you do a presentation, you can put the link up and you say, hey, all our code, all our experiments is online, it's here, done, right? You have a showcase of what's going on, and people can come back to your GitHub and you will see the projects. And then the last thing I want to mention is this is going to be recorded, and each team, I will cut the video down to however length that you are doing and you're talking, and then upload on YouTube, just like what I did for the previous group. And the same thing for showcase, if somebody asks if, in college representation, you want to attach a link, please do so, and I'll back you up with a story. All right, so with that being said, let me send out the survey. Let me know, if you're learning anything, if you're not learning anything. Any questions? Anything you still want to learn? I think if I would structure this course again, of course, 2 weeks is kind of like pretty tight, right? I want to teach as much as I can, but unfortunately, I only have 2 weeks, and I also want to give students a project. We can't just not do anything, right? I have to give students a project. So that unfortunately means that the lecture time will be limited. Comparing with a couple of the important concepts that we're teaching, linear regression, logistic regression, I don't think you can get away with that. If you don't teach that, then you don't have anything. People are gonna ask questions. Well, what is a forward propagation? And they're gonna be like, it's a linear additive, and they're gonna like, oh, what's a linear additive? Well, it's linear regression. So unfortunately, those things we can't skip. So I understand that sometimes people are very passionate about certain field that perhaps require knowledge of way above that of high school students. Let me know if that's the case. I'll help you out as much as I can. Yeah. So in regards to that, just let me know what I can do in a survey to make this class a little bit more interesting. And tomorrow, we'll come back. We're probably gonna leave like the first 40 to 45 minutes just to make sure everyone's wrapped up and make sure that you have your slides ready, GitHub ready, and you're ready to talk. I think one student will be absent tomorrow. If that's happening or if something emergency happens, let me know. That's no problem at all. The only thing I would recommend is within team, you guys kind of work it out, right? Because if one guy is out, then you guys need to work it out who's covering his part. That's the only thing I ask for. Other than that, I think it's pretty straightforward. Everyone knows what their project is, and everyone has code, everyone has experiments. I think it's pretty straightforward. So yeah, with that being said, let's just stop here. I'll stay here for more questions, and have a good night's sleep. And tomorrow we'll come back. We'll get a presentation started, and Sam and I will be both taking notes and reviewing your presentation. And this is kind of like the last chance that you let us know how things work, and the things that you learn, things you want to learn, let us know. With today's survey and tomorrow's survey, just let us know. And also, for recommendation letter, this is the last 2 survey, right? Anything you want me to write on recommendation letter, now will be the chance. Okay, no, we're not sending more surveys because survey is kind of annoying. Me personally, I'm kind of annoying at survey as well. All right. So with that being said, that's it for today. We can drop off early, and I'll see all you guys tomorrow.